Okay, so today we're going to take the opportunity to summarize Newton's 3 laws of motion, which all circle around force and how they interact in terms of motion and acceleration of an object. So Newton's first law, they all have kind of their own theme, and Newton's first law of motion is the law of inertia. Inertia was a term that you defined in your vocab list, and inertia is another way of saying an object's mass. So the more mass something has, the more inertia it has. If you imagine you're driving down the interstate and you have a bug coming towards you, you can imagine the bug gets splattered against the windshield. That's because your car has more inertia than the bug. It has more mass, and so unfortunately the car is going to win in that situation versus maybe the fly that you collided with. And so another really important place that you see this is in a lot of car safety. So in that middle example, it tells you that when the car stops, your body remains in motion, and that's why you need a seatbelt to keep you from flying into the windshield. So if you have ever been in a car accident, or maybe have done bumper cars, for example, you know that when you collide with something, your body wants to continue to move forward. So let's say you're in a car accident and you were going 30 miles an hour and you rear-ended someone. What happens there is that when you hit that car had a force applied to it, and it suddenly comes to a dead stop. However, no force acted upon you, and if you don't have a seatbelt, you continue to move forward at that same 30 mile per hour speed. And so you have to have a force act against the mass or inertia of your body in enough to bring you to a stop. And that's where your windshield or maybe your dash would stop you. So what a seatbelt does is it applies that outside force back against you that doesn't allow you to move forward. And so again, that's where a seatbelt becomes really important, because your body has inertia and you don't have enough force to exert against a dash to bring your mass to a stop. Okay? Newton's second law of motion we've calculated it now, but we're going to talk about what does that formula actually tell us besides just numerical, what does it represent? So we know that force is equal m times a, or mass times acceleration. So what that means is that if you increase mass, you have to increase your force to get the same speed out of it. That's the example on the middle there with the shopping cart. If you fill up that grocery cart, you need to exert more force to accelerate it at the same speed as which you were accelerating it when it was empty, because there's more mass in it. Same thing on the right-hand side with the sports car versus the minivan. You can probably imagine that sports car is going to pass the minivan quite easily. A couple reasons why. It has less mass than the minivan, and it's able to generate more force through the type of engine that it has. And so that's where we can see Newton's second law of motion. The last one is known as the action-reaction forces. Okay? And so for every action, there's an equal but opposite reaction. Okay? So a good example that you are all experiencing right now, because most likely you're sitting down, is like the example on the left-hand side when you're pushing on the wall. That's no different than you sitting on an object. So your weight is a force, okay? So that's where your mass is your inertia, okay? So you have, let's say, more inertia, you have more mass than, say, your textbook, for example, okay? So if those two were in an accident, it would take less force to stop the textbook than it would take you to overcome your inertia. Now, weight is a downward force because gravity is a downward pull on your body, and it's acting because of your mass. So as you sit on, again, whatever object you're sitting on, your action force is your weight pushing against your chair. You don't go flying down to the floor, and your chair doesn't send you flying through your ceiling, and that's because you have a reaction force that's equal but opposite. So notice that it shows balanced forces there, that for every action, it's equal and opposite. And so you don't have motion in this particular example. In the other two examples, you have motion because of where the action and reaction forces are being applied. So in the skateboarding example, and I don't necessarily like where the arrows are pointing, but you exert an action force. It's downward as you push and kind of pull your foot back. So that's against the ground. The reaction force isn't really pushing on you necessarily in terms of your foot, but where that reaction force is being applied is against the wheel of the skateboard. That's what allows you to accelerate forward. If you've ever been on a canoe, some kind of boat, even like a floaty in a pool, and you try to get out of it and back onto ground, here's a good example of action-reaction. So as you apply an action force to step forward back onto ground, the reaction force is applied to the boat, which then allows it to move backwards. So again, to summarize this, Newton's first law of motion is inertia, that an object in motion is going to stay in motion until an outside force acts on it. And if something is at rest, it's going to stay at rest until an outside force is applied to it. Newton's second law is the F equals ma equation. So the more mass something has, you then have to apply more force to accelerate it. And then Newton's third law are these action-reaction. So what we're going to do next is I have a couple examples. We're going to determine what law is being applied there and give you a short description of what's going on.